So today we're going to be going over lesson 2.04. Typically I'll post the live class recording for this, but just in the interest of speed today, getting all of them done, I'm going to do a separate recording for this one. So on these first problems it says, simplify the following exponential expressions so that there's a single positive exponent. Okay, so our first problem here is 3 squared times 3 to the 5th. We're going to need to use exponent rules on this. We'll remember we said x to the a times x to the b equals x to the a plus b. We might have called those m and n before. And we also said that x to the a over x to the b is going to be x to the a minus b. So we're going to be using those rules here. So 3 squared times 3 to the 5th means we're going to add the exponents since we're multiplying. This will be 3 to the 2 plus 5, which is 3 to the 7th. The second one, 5 to the 3rd over 5 squared. This is going to be 5 to the 3 minus 2, because we're using this rule. We're dividing, so we're subtracting the exponents. 3 minus 2 is just 1. We get 5 to the 1, which equals 5. Anything to the first power is itself. Now 17 to 0, this was a special case we talked about before. Anything to the 0 is 1. And sometimes it can be hard to remember that, but let me show you an argument for why this might be the case. If we use this rule right here, our division rule, and I say 17 squared over 17 squared. Well, by this rule, we're going to say the exponents subtract, so we're going to do 2 minus 2. This will be 17 to the 2 minus 2. And then 2 minus 2 is 0, right? So this will be 17 to the 0. But we also know that anything divided by itself is 1, right? 2 divided by 2 is 1, 5 divided by 5 is 1, and 17 squared divided by 17 squared is 1. Those will just cancel out, basically. So if we use transitive property of equality, we can see that 17 to the 0 is the same as all of these things, which is the same as 1. So just some more evidence for us to remember why anything to the 0 is 1. On number 4, we're going to combine several of these rules. So remember, we're multiplying. These will be multiplying across the top, and then we'll be dividing and dividing. Multiply, multiply, divide, divide. So when we're multiplying, we add, so that'll be 5 plus 3. And when we divide, we subtract, minus 2 minus 4. 5 plus 3 is 8, minus 2 is 6, minus 4 is 2, so that'll just be 7 squared. Now some people did it a different way, or in a different order, where they simplified this fraction first and then this fraction first. Let's try that way and see what happens. If we try the second method, so this would be 5 minus 2, and then we multiply 7 to the 3 minus 4. 5 minus 2 will be 3, 7 to the 3, times 3 minus 4 is going to be negative 1, so 7 to the negative 1. And then we can just add those two together, right? We're multiplying, so we add them. So this will be 7 to the 3 minus 1, which is still 7 squared. We get the same answer we got before, which is great. Okay, so for number 5, we're going to do the same process. We just have to keep in mind we've got a negative on the top here. So we're going to take the same base. We have the same common base of 3. We add the exponents because we're multiplying here. So negative 2 plus 6, and then we subtract the one we're dividing by. So we subtract 2. Negative 2 plus 6 is positive 4. Minus 2 is positive 2. This will be 3 squared. That one, the only tricky part is just keeping track of all these negatives. This one's going to be negative, And then this one's going to be negative 2 because we're dividing by it. So our answer there is 3 to the negative 2 plus 6 minus 2, which equals 3 squared. So now let's take a look at these next problems. It says simplify each square root by factoring out any perfect squares. And they gave us an example here. So root 8 is the same thing as root 4 times 2. We're just factoring that out. 4 times 2 is the same thing as 8, which is the same thing as root 4 times root 2. And then 4 is a perfect square, so we can square root that to 2, and then the root 2 stays the same. So this is going to be a process called prime factorization, and you may or may not have seen this before, but that's okay, we'll just figure it out now. So what we're going to do when we prime factor a number is we're just going to look at that number. In this case we have 75, and we're going to say to ourselves, what do I think I can divide evenly into 75? What can I divide 75 by and get an integer? Well, it ends with a 5, so I bet we can divide by 5. Let's see what happens there. So I just take my calculator, do 75 divided by 5, and I get 15. So I'm going to draw a little tree here where I say 5 times 15 equals 75. These are called factors of 75 because you can multiply them to get it. So now I look at the bottom of my tree and I say, are these primes, meaning nothing else can divide into them evenly other than itself in 1, or is there another number I can divide this by? Well, 5 is prime. 5 doesn't have any other divisors, but what about 15? We know that 15 is 3 times 5, so I can write this as 5 and 3. And 5 and 3 are both primes, so we can now say that the prime factorization of 75 is 5 times 5 times 3. Now the reason we would do this is because we're going to write this like this. Root 75 equals 5 times 5 times 3. But we know that 5 times 5 is a perfect square. So this is the same thing as 5 squared times 3. Now, if we split those out and give them their own root, like so, we can cancel this root and this square. So then we just get 5 root 3. So square root of 75 simplified, we pull out this perfect square factors, we get 5 root 3. All right, let's look at 63. Let's do another example. What do you think you can divide 63 by? Well, maybe 3. 3 looks like it would go into 6 and 3, so let's try 3 in my calculator. 63 divided by 3 is 21. All right. So we can do 3 and 21. 3 is a prime number. How about 21? Is that divisible by anything? Well, we might remember that 21 is 3 times 7. So we'll go through the same process here. These are all primes now. 3, 3, and 7 are all primes. We can do 3 times 3 times 7. We get root 3 squared times 7. We split out the root. The square root and the square cancel. And we get 3 root 7. So now let's look at root 18. What can we divide 18 by? Well, whenever I see an even number, I always say 2. I'm always going to try 2 if I see an even number. So let's do that. Let's do 2, and 18 divided by 2 is going to be 9. So 2 and 9. 2 is a prime. How about 9? Can 9 be divided by anything evenly? Yeah, 9 is 3 times 3. So let's write this one out. This will be 2 times 3 times 3. Same thing as 2 times 3 squared. Give them their own roots. We can cancel the square and the square root. And we get root 2 times 3. You may also see this written as 3 root 2. We often put the whole number out front, but these are the same answer. They're both correct. You don't have to write it one particular way. You just may often see it this way. So now let's look at our final problem on this page, 98. And just like in the previous one, this is even, so I'm inclined to be like, well, let's try 2. Let's try 2. And then in my calculator, 98 divided by 2 is 49. So 2 is prime. What about 49? Is 49 divisible by anything? 49 is a perfect square, right? It's 7 times 7. So we can say our prime factorization now, because these are both primes, 7s are primes. Our prime factorization of 98 is 2 times 7 times 7. We're going to write this as 2 times 7 times 7, which is the same thing as 2 times 7 squared. Separate out the root. The square root and the square cancel, and we get square root of 2 times 7, which you may also write as 7 root 2, either way. Now we had a question in class, let's go back to this one really quick. We had a question that said, what if we didn't do it 2 times 9? What if we instead started with 6 times 3, which is another valid way to get to 18, 6 times 3. Well, in that case, we'd say 3 is prime, and then 6 is also 2 and 3. So our prime factorization here would be 2 and 3 and 3. If we look at the way we got it with 2 and 9, we get 2 and 3 and 3. It's exactly the same. Same numbers, 2 and 3 and 3, 2 and 3 and 3. So the prime factorization of any number is actually unique. No matter what method you take to get there, you should get the same set of numbers. Pretty cool. All right, let's move on to the next page. This says, for each geometric sequence below, geometric, we know we're going to be multiplying, fill in the missing values and then write an equation for the pattern. All right, so we remember how to do this. We said we're going to take steps up each time, and we know we're going to multiply by the same thing every time. So we say, we'll just call it R for ratio, common ratio. And let's see, there are 1, 2, 3, 4, 5 of them. So we can say 2 times R to the 5th, because there are 5 of them, equals 64, right? Because we're just going to multiply 2 times R 5 times, and that's going to be 64. Solving for R, we'll divide by 2, divide by 2. We get R to the 5th equals 32. We're going to need to 5 root both sides now. 5 root that, 5 root that. The 5 root and the 5th will cancel. And we get R equals, let's see, we'll put that in my calculator. 5 root 32 is going to be 2. R equals 2. So that is our common ratio every time here, multiply by 2. So we're going to use that to fill in the table. 2 times 2 is 4. Times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 128, times 2 is 256. And then for our equation, we have our good old geometric equation that looks like this. F of n equals a times b to the n, where a is our value at 0, and b is our common ratio. We've already figured out the common ratio. What's our value at 0 here? Let's see, we have a 1. We actually need to go back a step to get to our value at 0. So let's see, this is going to be multiplied by 2. So 2 divided by 2 to go back is going to be 1. So a is 1. So we'll get 1 times 2 to the n. We're just plugging this in, right? 1 goes in here, 2 goes in there. Maybe I'll write an n that actually looks like an n. There we go. 1 times 2 to the n. And then anything times 1 is itself, so we can just drop that actually. And we get 2 to the n as our function. That's our overall function for this geometric sequence. Let's look at the next one. We're going to use the same method. Again, we're going to multiply at each step. And we can call it R for common ratio. So there are 1, 2, 3, 4, 5 again. So we're going to get 972 R to the 5th equals 4. Because we started here, we multiplied by R 5 times, we got 4. Now we're going to need to divide both sides by 972 to get R by itself. We get R to the 5th equals, now this is going to be a tiny number, right? 4 divided by 972 is going to be super small. It's going to be a fraction. I get 0.00411522 in my calculator. But I'm actually just going to leave it as this fraction for now. So I can 5th root this and 5th root this. The 5th root and this 5th will cancel, and I get R equals, and I just need to put this whole thing in my calculator. 5th root of, open paren, 4 divided by 972, close paren, and I get R equals 0.3333 forever. Sometimes we write this as 3 bar. That just means 3 repeating forever. Are we familiar with this particular decimal? Do we know what fraction that is? We sure do. 0.3333 forever is just 1/3. So our common ratio here is 1/3. That's what we're going to be multiplying by every time. Remember, multiplying by 1/3 is the same thing as dividing by 3. So 972 divided by 3 is 324. Multiply by 1/3, that'll be 108. Next one will be 36, multiplying by 1/3. Next one will be 12. And our last one will actually end up being a fraction, but that's okay. 4 divided by 3 is 4/3. That can be our 7th term. And now we're going to use this same form for the equation, f of n equals a times b to the n. Where a is our value at 0. We haven't figured that out yet. We have to go back one step. Back one step. Okay, so it looks like we're going to have to divide by 1/3 now, or multiply by 3. 972 times 3 is 2916. So A is going to be 2916, and B is going to be our common ratio, which we decided was 1/3. So overall, our function is going to be 2916 times 1/3 to the n. That's our equation. This was our equation up here. It's a little bit separated out, but there you go. F of n equals 2 to the n. Let's go on to the next page. So number 12 says, fill in the missing values based on the growth described, then write an equation for the pattern. And number 12, it says the values are tripled at each whole year. Okay, So we actually know how to do this already, right? We know that this is tripled, so it's going to be geometric. We're going to be multiplying by 3 at each whole year. The only problem is we now have half years to deal with too. But we can do the whole years first, because that already makes sense to us. Multiply by 3, multiply by 3. Make a bigger loop here. Multiply by 3, and multiply by 3. So let's just fill that in. 2 times 3 is 6. 6 times 3 is 18. 18 times 3, I believe, is 54. Yep, 18 times 3 is 54. And then 54 times 3 is 162. Now, before we even fill in these other values, we know how to write this equation, right? We already know this is f of n equals a times b to the n. Oops, not squared, b to the n. A is our value at 0, right there. A is 2. B is our value of our common ratio. So we multiply by each time, so that's going to be 3. So we already know that our equation up here is going to be f of n equals 2 times 3 to the n. Now we just have to figure out what these in-between numbers are. I'm going to use a different color. Maybe let's use blue. So we remember from the previous lesson that we're going to use the same method. We're going to multiply at each of these steps, but it's going to be a different number now. It'll be a different number than those bigger steps. So let's just look at this first one, getting from 2 to 6. If we call this r for ratio, we know we're going to have to multiply by r, and we get 2 times r equals 6. We'll do that over here. 2 times r squared, right? That's what r times r is. 2r squared equals 6. Divide both sides by 2. We get r squared equals 3. We square root both sides, and we get r equals, oh, well, root 3, that doesn't simplify, does it? It's not easily divisible, but that's actually just fine. Root 3 can be our factor here, what we multiply by. So we're going to try multiplying by root 3. 2 times root 3 is just 2 root 3. And if we multiply that by root 3 again, we'll get 2 root 3 times root 3. Anything times itself means we're squaring it, right? So that's going to be 2 root 3 squared. The square root and the square cancel. We get 2 times 3, which is in fact 6. That is what we got. So that is the correct ratio, or the correct factor rather, to multiply by at each step. Now all we have to do is just multiply by that same factor at each step. So this is going to be 6 times root 3, which is 6 root 3. We multiply by root 3 again, and we get 18, because those roots are going to cancel. We get 6 times 3 is 18. Multiply by root 3 again, we get 18 root 3. Multiply by root 3 again, we get 54, because 18 times root 3 will be root 3 squared. The square root and the square will cancel. We get 18 times 3 is 54. One more step, we get 54 root 3. So that fills in everything we needed to do here. We have our table filled out, we have our equation, and we can move on to the next one. So here's the next problem, problem 13, and it says the values are tripled at each whole year. And this is the same pattern as the previous problem, it says, but the fractions are different. Oh, so this is the same table we just looked at. It's just that now we have, looks like we have 2 numbers in between the whole numbers instead of 1. Well, that's actually pretty cool, because we know that we made this equation. I'm going to grab my pen again. We know that we made this equation based on the whole numbers, not on the divisions in between. So we can actually use the same equation we used last time, right? We don't have to derive it again. We just use this f of n equals 2 times 3 to the n. I love it when we don't have to do work again. F of n equals 2 times 3 to the n. Remember, we got that because we looped from whole number to whole number and did multiply by 3 each time. Multiply by 3, multiply by 3. So 2 times 3 is 6. 6 times 3 is 18. Our value at 0 was 2, and our common ratio is 3. So that's how we got that equation. So now, once again, we will change colors. We need to figure out what these smaller steps are. So maybe we'll call those r, like we often do, r. So 2 times r times r times r, that's going to be r cubed, equals 6. 2r cubed equals 6. We'll divide both sides by 2 to get r by itself. We get r cubed equals 3. Now we need to cube root both sides. And we get r equals, well, cube root of 3 doesn't simplify, much like square root didn't. Cube root of 3 is just the cube root of 3. So we would multiply by the cube root of 3 over here. That's just 2 cube root of 3. Now what happens if we multiply by cube root of 3 again? We would get 2 cube root of 3 times cube root of 3. This is a square, right? Something times itself is a square. So that's just going to be 2 cube root of 3 squared. Now typically we'd want to cancel these, but this has a base 3 and this is a square too. So those actually don't cancel. We just leave it like that. This will just be our answer for this next box. It's going to be 2 cube root of 3 squared. If we multiply one more time, cube root of 3, we'll get 2 cube root of 3 squared times cube root of 3. Okay, so now we have squared. Now we have another one. This is going to turn into a cubed, and we will get 2 cube root of 3 cubed. So now the cube root and the cube will cancel, and we get 2 times 3, which is in fact 6. That is what we were looking for. So now it's just really going to repeat this pattern. We're going to take the whole number times cube root of 3, so that'll just be 6 cube root of 3. We'll multiply again by cube root of 3, and that's going to square this, so 6 cube root of 3 squared. And then the third time we multiply it, that cube root drops out, and we get 6 times 3 is 18. We just keep following that pattern. Multiply by cube root of 3, we get 18 cube root of 3. One more time times cube root of 3, and we get 18 cube root of 3 squared. All right, let's go on to the last problem. Same instructions, fill in the missing values and write an equation. This says the values grow by a factor of 4 at each whole year. Let's do that one. So once again, we'll just start with the whole years because we know how to do that. Multiply by 4. 2 times 4 is 8. Multiply by 4 here. 4 times 8 is 32. Multiply by 4 there. I don't know what that is. I have to do that in my head or in my calculator. 32 times 4 is 128. And 128 times 4 is 512. So once again, we don't need those in-between values to write the equation. We already know how to do that. F of n equals a times b to the n. A is our value at 0, so that's 2. B is our common ratio, so that's 4. And our overall equation is f of n equals 2 times 4 to the n. So now let's find our in-between values. So we're going to go from 2 to 8. Looks like we're going to multiply by r twice, so this will be 2r squared equals 8. 2r squared equals 8. I'm going to divide both sides by 2. I get r squared equals 4. Square root both sides to get r by itself. The square root and the square cancel, and I get r equals, well, look at that. The square root of 4 is actually 2. It divided out evenly, so that's really nice. We can now just multiply by 2 each time. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. This one worked out really nicely. Times 2 is 64. Times 2 is 128. This will be 256. And our last times 2 is 512. So this last problem was really nice, divided out evenly. And that is all of assignment 2.04.